absolute value. What does an absolute value graph look like? A V. So I've told you exact points, at least 3 of them. So we have the absolute value of 0 is 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2. You can give me more. We graph the parent function as a dashed line. Okay, my transformation. If I try to just look at this and identify the transformation, we have a couple things going on. The fact that I'm taking my x times something is a horizontal transformation. But then that minus 4 is also going to move it how? To the right 4. So the stretching and shrinking horizontally can get complicated. My suggestion, if you look at 2x minus 4, can't we factor that? Okay, what could we take out? 2. Now you can't always just pull things right out of an absolute value, but isn't the absolute value of 2 equal to 2? So I'm going to factor that 2 out, and because it's a positive number, I could bring it out in front of my absolute value. So now if I'm trying to decide what my transformations are, this 2 out in front would be what? Vertical stretch. It's outside, so it's y. Does what it says. So we're going to take all of our y's times 2. And this x on the inside will move our graph right 2. Inside is x, and it does the opposite of what we say. So a subtraction moves it in the positive direction. Now, it is up to you how you do this. So you might be able to just work through it and say, okay, here's 0, 0. If I move it right 2, I'm here. The y value of that is 0 times 2 is still 0. Okay, if I take this point, shift it right 2. My y value is 1. If I take that times 2, it's now at 2. Okay, if I took this point, right 2. My y value is 2 times 2 is 4. Okay. If I take my negative 1, 1. If I move it right 2, I'm here. The y value is 1 times 2 is 2. Take this point, right 2. My y value is 2 times 2 is 4. And so we see we are getting a skinnier absolute, oof. I swear I can draw straight lines, but my slate has been glitching a lot this year, and I can draw straight lines on it this year. Okay, now, if that's hard for you, you don't have to do that. Some of us can think of it this way, some of us it's harder, and that's okay. If you take these exact points, we know, talked yesterday, outside is y and it does what it says. So it's saying take your y's times 2. If I take my y's times 2, I end up with these points. Okay, and then I have to move them all to the right 2. So if I'm at 0, 0, right 2, I get here. Right, this point was at 1, 2, right 2, and I'm here. Negative 1, 2, right 2, and I'm here. I get the same final points. So if the stretching and shrinking is confusing for you, write out some ordered pairs. Multiply to do your stretching or shrinking, and then move it left, right, up, down, however else we need to. Is that okay with everyone? Let's look at another. All right, what's my parent function? Square root. Can I do the square root of negative numbers? No, those give me imaginary. So the square root of 0 is 0. The square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. So that's my graph. What will the 1/2 do?
Compress it.
vertical compression or shrink, however you want to call it. What would this plus 2 do? And the minus 3? Okay. So, again, if you struggle with that compressing, you're welcome to write out your points. But you don't have to. It's outside. Outside changes y, does what it says. So if all I'm doing was the compression, I would just be taking all of those y values times a half. But that's not all. So I would have 0, 0, and now I need to move it left 2 and down 3. Okay, if I took my 1, 1, that becomes 1, 1/2, left 2, down 3. Okay, this will go to 4 1s, left 2, down 3. This will go to 9 1.5, left 2, down 3. So we get this graph. Try a couple more. What is the parent function this time? X squared. So 0 squared is 0. 1 squared is 1. 2 squared is 4. Negative 1, 1, negative 2, 4. If you wanted, you could go 3, 9, and negative 3, 9. My requirement is 3 at a minimum. But more is better. Okay. From here, what will my 3 do? Stretch. What's this plus 2? And the plus 1. Up and down needs to be the last thing you do. If you try to move it up 1 and then take your y's times 3, that will mess you up. So I'm going to save that for the end. Let's see if we can talk through this one without writing out ordered pairs. So if I'm at 0, 0, okay, the 3 is outside. Outside changes y, does what it says. So if I take my y times 3, I'm still at 0. And then I go left 2, up 1. Okay, here, my y value is 1. 1 times 3 is 3. Then I need to go left 2 and up 1. Okay, if I take my 1, 1. Currently this y value is 1 times 3, we'll move it to 3. Then I go left 2, up 1. So we kind of see we're getting this skinny graph moved to the side. That would be enough points, but we could do more if we wanted. However, this one's at 4. When I take it times 3, it's going to be at 12, so it's going to go off my graph. So we see we're getting this. I guess I haven't been doing it, but if I asked you to give me domain and range of that graph, could you? What's your domain of that final one? Okay, the range? The final one would be 1 to infinity. Alright, why don't you guys try this one? Draw the parent function and think about the transformation. So 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, but negative 1 to the third is negative 1. Negative 2 to the third is negative 8, so we're getting this chair. Alright, what does the negative out in front do? Flip or reflect over, it's like making my y's negative. So it flips it over the x. The minus 2 would take it right 2. And the plus 1 would go up 1. Again, up and down is the last thing we do. I saw several people writing out ordered pairs, which is great. If you need to do that, do it. All this negative does is changes the sign on all of those y's. So it becomes like this. Okay, so if I think 0, 0 doesn't go anywhere, when I flip, then I go right 2 and up 1. 1, 1 goes to 1, negative 1, right 2 and up 1. 2, 8 would go to 2, negative 8, right 2 and up 1. Negative 1, negative 1 goes up here, right 2 and up 1. And negative 2, negative 8 would come up here, right 2, up 1. So then we get our final graph. Questions on those? Did you guys get it? The next slide, I gave you some graphs and asked you to do the transformations. I didn't give you the equations. Now, I used to do those to prevent people from using their graphing calculator and everything. I guess you guys don't get a graphing calculator on a test anyway, so it wouldn't really benefit you. But it's good practice. What's the minus 2 going to do? So we are essentially just finding some nice points on here. And we're going to drop every one of those points down 2. Same shape, make sure you're picking enough points that you have your shape still. Let me drop that in. I think I'm going to only do part of these. Let's go to D for the last one. What does the negative in front do? What's the minus 2? And then the plus 3. Okay, so if I take this point and reflect it, it's on the axis, so does it go anywhere? And then right 2, up 3. Okay, if I take this point and reflect it, where does it go? Negative 2. Go right 2, up 3. If I take 0, 0 and reflect it, doesn't go anywhere. Right 2 and up 3. This looks like 1, negative 2 and a half. So we'll go up to positive 2 and a half. Right 2, up 3. And 3, 2 will go to 3, negative 2. Right 2, up 3. So you don't have to have a full equation, we just need a graph to be able to apply our transformations. Do we have any questions about transformations? The last piece that we need to talk about is symmetry of a graph. So when I am talking about symmetry, you know, like you've heard lines of symmetry before, probably in an art class or something. It's a line you can fold your graph over and it would overlap itself. Okay, so sometimes we have cases where a graph is symmetric to the y-axis. For instance, our parabolas. Okay, would you agree that a normal parabola, if you fold it over the y-axis, those two pieces overlap? So if we think about that, the points, we have like 1, 1, negative 1, 1. We have like 2, 4, negative 2, 4. And so what happens, it's symmetric over the y-axis if both a positive and negative x have the same height, the same y value. So we have all these definitions of symmetry. I'm trying to kind of explain what they mean. If it's symmetric across the y, if your x is positive or negative, y is going to be equal. Okay, what would be another graph that we've done that's symmetric across the y-axis? Absolute value. Whether you put in a positive x or a negative x, you get the same thing for the absolute value. Now, if it's symmetric to the x-axis, we haven't seen those because, is this a function? No. So we've been graphing functions, that's why we haven't seen a lot of them. But those would have points like 1, 1, 1, negative 1. 2, 2, 2, negative 2. So the x's are the same, but the y's are opposite. So this tells me if it's symmetric to the x, both the positive and negative y give you the same thing. The third type of symmetry, this one we do see with functions. Think about our x cubed. If I fold this over the y and then the x, would it overlap itself? If I take two flips over the y, if we fold over the y, it looks like this. Then if I fold that dashed one over the x, does it overlap where it started? That's called symmetry to the origin. If you think about these points, we have 1, 1, negative 1, negative 1. We have 2, 8, negative 2, negative 8. What's true about them? Both the x and y are opposite. So if it's symmetric to the origin, if both x and y are changed, you'll get the same thing back. So there are a lot of different ways to find symmetry. We can look at graphs. We can, if it's written as a function, use negative for our x's. But the easiest way, if we're just looking at an equation with both an x and a y, is to check each type. So if I wanted to check symmetry to the x-axis, okay, we said if it's symmetric to the x-axis, both a positive and negative y would give you the same thing, right? So if you want to check symmetry to the x, you replace y with a negative y and see if we get the same thing back. Is the absolute value of negative y the same as positive y? Yeah, so this is equivalent. So this graph is symmetric to the y-axis. Sorry, x-axis. Because a positive and negative y give you the same thing. If I want to check the y-axis, what would I do? We said if it's symmetric to the y, both x and negative x give you the same thing. So we replace x with a negative x. If I do that, is there anything I can do to turn that back into my original? No. So this one is not symmetric to the y-axis. For origin, we do both. We replace y with negative y, x with negative x. So if my x is negative and my y is negative. Okay, the absolute value of negative y is the same as the absolute value of positive y, but can I get rid of the negative on the outside? No. It is possible for a graph to have more than one kind of symmetry. Actually, it can only, if it has two, it will have all three. So it's either going to be no symmetry, one, or all three. But you can't just check one and stop, because you could have more than one. All right, let's try a couple more. I may not do all of these, but we'll do a couple. If I do b, so if I want to check my symmetry to the x-axis, you're essentially just replacing the opposite variable with a negative. If I make my y negative, is there anything I can do to turn that back into the original problem? We can divide it. That would move it over here. Is that going to give it back the original? No. So this one is not symmetric to the x. You want to check the y. You make your x negative. What happens if you cube a negative? What's negative 2 times negative x? Okay. Is that what I started with? I've got my y, but the other side is flipped, isn't it? So it's not the same. If I want to check origin, we do both. So I have negative y equals negative x cubed plus 2x. Okay. Is there anything I can do to turn that into the original? I divide by negative 1. So then I have positive y equals positive x cubed minus 2x. That is what I started with. So this one is symmetric to the origin. Questions on that? Let's do one more. Let's check D. So how do I check symmetry to the x-axis? Make your y negative. What happens if you take negative y times negative y? Then a positive. Is that what we started with? Yes. So this one is symmetric to the x. If I want to check my y, what do we do? But a negative squared is positive. So again, that's what we started with, so it is a yes. Now if you were listening a second ago, you already know what's the origin going to turn out to be. Yes. If you didn't remember that and wanted to check it, we see a squared is positive. It's the same. This one has all three. What is the original graph? Do you guys know? X squared plus y squared equals 25? It's a circle with a center at, the radius is 5. Centered at 0, 0. And so it has all three types of symmetry. When things are written in function notation, instead of a y, we have an f of x. So we have a couple options. You could write it, change your f of x back to a y and do it the same thing. We can also just talk about what happens when we plug in an x. Sometimes when we're talking about functions, instead of saying symmetric to the y-axis or origin, they use the word terms even and odd. Even is the same thing as symmetric to the y. Odd is the same as symmetric to the origin. And I don't have a symmetric to the x because I'm talking about functions. and functions can't be symmetric to the x. So what I always remember, the O's go together. Odd, origin. If it's written in function notation, it's almost easier to check. If it's symmetric to the y, positive and negative x have to give you the same thing. Okay, if it's symmetric to the origin, we've said you have to flip both the x and the y. So that means if the x is the opposite, your y turns out to be the opposite. So if you plug in a negative x, you get the opposite back. So if that confuses you, you're welcome to do it just the way we have been. Otherwise, if it's written in function notation, essentially what we can do is just plug in a negative x. If we get back the original, then it's even. It's symmetric to the origin, or to the y-axis. If we get back the exact opposite of what we started with, that is an odd function, or symmetric to the origin. And anything else is needed. So real quick, looking at a couple graphs, can you tell me what kind of symmetry this has? So this one is symmetric to the y-axis, and another word for that is even. What's this one symmetric to? Origin. You'd have flipped twice. Symmetric to the origin, another word for that is odd. Alright, what about this one? It's odd again. Think about if you flip this over the y. This piece will come over, that piece goes over here. Okay, it looks kind of messy right now, but imagine if you only had those dotted ones. And then if you flip that over the x, will the dotted overlap the original? I think they will. So if I fold it on the x, they're going to hit each other. So this one is actually another odd. You have to flip over both axes to get back what we started with. And what's the last one? Odd again. Alright, so we'll try a couple just written in function notation and then I am done. So you could, like I said, if you prefer, instead of f of x, you can write y and do it the same way we were checking it before. The easier option, if it's in function notation, you change your x to a negative x. If you square a negative, it becomes, so I plug in a negative, I get the same as I started with. So both a positive and negative x give me the same thing. What does that mean? The next one. Plug in a negative. A negative x times negative x times negative x is still. Is that what I started with? No. Is that the complete opposite? Like I took the original times negative 1? No. So this one is neither. It has no symmetry. Now, could you also, like a and b, could you have graphed those and looked at the graph? Yeah, we know x squared is a parabola shifted down 5. Would that be symmetric with the y? And that's even. X cubed is a chair, but when you shift it down 1, it loses that symmetry. Last one. If I plug in a negative for my x, so this would be a negative cubed is still negative. So I get negative 5x to the third minus negative x is plus x. Is that what we started with? No. Is that the exact opposite? Like if I took the original times negative 1? Yes. So that means if I have an x and y, negative x, negative y is also on there. So that is So that is the end of this section. Yesterday I gave you that handout, and you have time to work and ask questions.